Hi everyone, so welcome back. What we're going to do today is continue with our discussions on alkyl halides. So we are in chapter 7 of the Klein textbook, and we are discussing alkyl halides. And what we've done so far is we've talked about a reaction. Well, what we did is we kind of discussed, I gave you a general overview of the type of reactions that alkyl halides do. So they do substitution reactions and they can do elimination reactions. And then we went into the specifics of the bimolecular nucleophilic substitution reaction, which we also call the SN2 reaction. That's how it's abbreviated. So, and we looked at what are some factors that control or that are important as far as the SN2 reaction is concerned. So you need an alkyl halide, you need a nucleophile. Now, the nucleophile in SN2 reactions, it's usually a strong nucleophile, okay? That's the kind of nucleophile that does substitution, SN2 reactions to be specific. And then what we saw is, with respect to the alkyl halide, the methyl halides are the most reactive, the tertiary alkyl halides do not react. Secondary alkyl halides are slow in substitution reactions. And then we looked at like other parameters that affect an SN2 reaction, like for example, the solvent. Polar aprotic solvents, they help SN2 reactions, okay? So what we're going to do today is discuss an elimination reaction. Now, I do want to mention that we are not done with all substitution reactions. There's another substitution reaction that we will go back to. But to contrast the SN2 reaction, I'm going to talk about an elimination reaction, which is kind of related, but it's different from SN2. So I think we have to be able to differentiate the two, identify some differences that would help us predict if you're given a set of reactants, whether it's a SN2 or an E2. So we'll go into all of those details later. Okay. So again, this name, now it should be easy, but we will come back, fill in what specific reaction are we talking about. Okay. To review, elimination reactions, to give you an example, let me pick this molecule here, and let's say we have an alkyl halide, and you react this alkyl halide with a base, and a strong base, okay, sodium methoxide. Now, right now, I'm including these charges, but when you look at these molecules in the textbook and on a quiz and an exam, these charges would not be there. But we've seen this over and over again throughout the acid-base chapter and now. So get into the habit of basically realizing that whenever you have a metal ion like sodium or potassium, or could be lithium, any of those things, when you have those with like an oxygen or a nitrogen or something, it's an ionic compound that we're talking about. It's a Na plus and O minus. Okay, so when we react this, now we used this as a nucleophile, strong nucleophile for an SN2 reaction. But in an elimination reaction, this behaves more like a base. Okay, so it's a strong base. We will come back to that, and I will show you once we go through the mechanism. When you take these two and react them, and the solvent in these reactions is usually a polar protic solvent now that we know these terms. Okay, it's a polar protic solvent. And the solvent is usually the conjugate acid of the base that we are using, okay? So we are using this as a strong base. That's the role that it's playing in this reaction because it's an elimination reaction. The same molecule in an SN2 reaction was a strong nucleophile because it is a strong nucleophile also. So a base and a nucleophile, they are the same, but what they do is like we define them as a base or a nucleophile based on the act that they do, the role that they play. So it's a strong base. When we do this, the solvent is usually the conjugate acid of the base, so methoxide. So the conjugate acid would be when you add a proton to it. So the proton would go to that oxygen. So basically methanol, that would be a good solvent for this. And for E2 reactions, you usually heat these reactions. And what happens is when you do this, you get an alkene as your product. And plus, there will be sodium bromide in this case. And we are going to make methanol, but that is pretty much your solvent. That's the solvent that we are using under these conditions. Okay, so this is the reaction. So what do we know about this reaction? Okay, what are some things that we know? So so this is a strong base. So from kinetics, what we know is rate depends on concentration of the alkyl halide and concentration of the base. Okay, so it depends on the concentration of the alkyl halide as well as the base. So it has a dependence on both concentrations. Rate increases when, or sorry, I think I should go specific. Rate doubles when concentration of alkyl halide or base is doubled. So since we've seen a scenario like this already, I'm just basically combining these two sentences into one. So essentially what we're saying is the rate is going to double when the concentration of the alkyl halide is doubled, and it's also going to double when the concentration of the base is doubled. So based on that, we can basically write a rate law. The rate law should be rate equals the rate constant times concentration of the alkyl halide times concentration of the base. And the power is 1. Okay, so the overall order of the reaction is 1 plus 1 equals 2. So that means it is a bimolecular reaction. Okay, RXN, I'm just going to use that abbreviation for reaction. So it is a bimolecular reaction. And overall, it is an elimination reaction because going back to some of the discussion that we had in SN2, realize that what's happening here is this is our alpha carbon, okay, the carbon which is connected to our functional group. And for this particular molecule, we have how many beta carbons? You might want to guess that, okay, because beta is a carbon that's connected to the alpha carbon. So we have beta here, this is a beta, and this is a beta. So there are 3 beta hydrogens in this, beta carbons in this molecule, sorry, and all of them are the same essentially, okay, because they're all connected to that alpha carbon, and there is nothing else that differentiates them. So they are all identical. Okay, they're not unique, they're all identical beta hydrogen. So essentially what's happening in this reaction is we're getting a double bond between the alpha and the beta carbon. And so what's happening is beta hydrogen now, because that hydrogen is connected to a beta carbon, we're going to call it a beta hydrogen. A beta hydrogen is lost. And plus this the halogen is lost. And that's why you're getting this double bond between the reaction. So overall, what we are losing in the reaction is an HBr. Okay, the H beta Br to be very specific. So it's a beta hydrogen and then the Br that's lost in the reaction. And that Br is in the sodium bromide. This H beta is actually in this methanol. That hydrogen that the methanol got, the methoxide gets, is this H beta. That is how this reaction works. Okay, so overall, this is an elimination reaction. Okay, so this is an elimination because we are eliminating a small molecule. And this is like elimination of alkyl halides. Elimination reaction is just a very general term, which would include any reaction in which a small molecule is lost from your starting material and you get to your product. Okay, it could be any. We're going to see another elimination reaction pretty soon in this chapter, where what's lost is not an HX in some sense, because this bromine does not have to be a chlorine. We could have started with a chlorine. This does not have to be a bromine. It could have been a chlorine or an iodine. And in that case, we would have lost HCl or HI. Okay, so this is an elimination overall. And it's a bimolecular reaction. So this reaction that we're talking about is an E2 reaction. We call it an E2 reaction, which stands for elimination bimolecular. Okay, now we don't usually call it elimination bimolecular, we'll call it bimolecular elimination. Okay, but E2 is how we will address it. We will call it an E2 reaction. And some of the key things that you want to notice here are the strong base, because that's something that's going to differentiate E2 from a related elimination reaction. A strong base is present in an E2 reaction. A strong nucleophile was present in an SN2 reaction. Okay, so that's the overall E2 reaction. Now, and the kinetic data basically helps us to predict that the mechanism, okay, again, compare it to the SN2 reaction. What we're seeing here is that the rate depends on the alkyl halide and the base. Those are our two reactants. And since these are both present in your rate determining step, because this rate law always relates to your rate determining step in some sense. I mean, for much bigger reactions, it's a composite of several things, but for simple reaction, it does tell you something about the rate determining step. So what this is saying is that both the alkyl halide and the base are present in the rate determining step. So based on that and some other evidence, because it's a little bit more complicated, I'm going to basically make it into like small bite-sized pieces, you know, so I'm going to upload a few videos on different aspects of this reaction, but there are some other things that help us understand what the mechanism should be. But I'm going to give you the mechanism right here. So I'm going to erase this portion, okay? And what we know is mechanistically both the alkyl halide and the base are present in the rate determining step. And essentially, the mechanism of this reaction, this is again a one-step or concerted process. It's a one-step or concerted process. And what happens is when you have that alkyl halide, since we are working with this H beta, and I could have picked any of the other H betas, and remember there are 3 hydrogens on that carbon, so they're all H beta. So in total, this molecule has 9 beta hydrogens, which are all identical. Okay, so I could have picked any one of those 9 hydrogens. So this is just a representative H beta we have. So what is going on here is the alkyl halide reacts with our base. And remember, the sodium is only balancing the charge, so we can leave it out of the mechanism itself. Okay, so what happens here is in an SN2 reaction, this would act as a nucleophile and go attack that alpha carbon. But in a E2 reaction, what happens is the base goes and deprotonates. That means it picks up that beta hydrogen. At the same time, the bond between H beta and C beta, the beta carbon and the beta hydrogen, falls into the space between alpha and beta carbons, and the halogen gets kicked out. Okay, now, in fact, I think it's fine for now, but we will look into some other things about the mechanism. Okay, there's something that's not exactly right about the mechanism here. Okay, not the arrow push itself, but there are some other stereochemical aspects that we will get into later. So we get this, and that's how we end up with this alkene, where we have a bond between the alpha and the beta, and plus we are going to make the methoxide with the H beta connected to it, and this bromide is going to finally end up with the sodium. Okay, so the sodium is always here, that goes with the bromide. So that's how we get to the product. So the mechanism is basically one step. It's concerted, and it involves 3 electron pushes. So there are 3 electron pushes that you're going to do in the mechanism of this reaction. Okay, so that is an overview of the E2 reaction. Now the subsequent videos, they will all look into aspects of the E2 reaction. Okay, like one or two factors that contribute to or control the E2 reaction, the ones that we can learn from. Okay, so this is an overview. We're going to stop right here. Well, actually, what we should do is we should maybe do another example now. Maybe we should, yeah, before we end, we should do an example. So as an example, let's say if we have that alkyl halide and we react this with sodium hydroxide. It's a nucleophile, strong nucleophile, but it's also a strong base. The solvent is going to be the conjugate acid of our base. So hydroxide, that means the conjugate acid is water. And we're going to heat this. Okay, so those are some things that you're looking for when we're talking about E2 reaction. So heat usually promotes elimination. Okay, now in this particular case, this is alpha carbon. This is beta. This is also beta. Notice how there's no beta hydrogen on this carbon because it has 4 bonds to it already. So there are no beta hydrogens. The only beta hydrogens are on that carbon. So that means when we do this reaction, the product that we will get is this. We will get a double bond between alpha and beta, and plus you're going to get water as side product, and you're going to get sodium sodium chloride, salt, along with that. Okay, that would be our reaction. And in terms of mechanism, if we had to show a mechanism for this reaction, what's going on here? So you have Br, you have alpha. This is our H beta. This is our beta carbon. So the base, which is hydroxide, this will deprotonate H beta. Electrons between H beta and C beta go into the space between alpha and beta, and then the bromine is going to leave. So that would be the mechanism of the reaction. But again, like I said, there are some stereochemical aspects that we're going to see in subsequent videos. And after that, we're going to change this electron push. This electron push is fine, but there are some stereochemical aspects that we need to keep in mind when we do an E2 reaction. Because that would be an example of an E2 reaction. So I'm going to stop this video right here, but go into like, please watch all the subsequent videos because they will look at different parameters that control E2 reactions, or that the other factors that we need to keep in mind when we're talking about acid reactions. Bye.